Go ahead.
All right, cool. So I apologize in advance. I'm still getting over a head cold that I got last week. So if I have to clear my throat as I go along, I'm sorry. So I am Mike Brim from Oak Ridge National Laboratory. I sit within the computing division that runs the Leadership Computing Facility. And one of the things we're seeing at the facility is that leadership class computing is increasingly used for scientific machine learning and artificial intelligence. Hold on a second, let me get rid of this, it's in the way. And currently, mostly what we're seeing is training, large-scale training type workloads where you have either high metadata operation rates for data sets that are composed of lots of small files, or you have large files where you need lots of high random read IOPS. And of course, the rates of these metadata operations or read IOPS only grow as these workloads are scaled up to leadership scale sizes, which is we define as like 20% of our largest machine. The problem is that Lustre, GPFS, other parallel file systems are designed for large sequential reads and writes. And so we do not see the ability of those systems on our current production systems to provide high rate metadata or random reads, primarily because these are patterns that lack temporal and spatial locality. And so lots of the design of parallel file systems relies on sequential caching, and you just don't see the benefits. Okay, it's not advancing. Let's try here. There we go. So historically, so in our past two leadership systems, Summit and Frontier, we've used no local storage. So NVMe devices deployed in each computing system node. And there are some advantages of this. So NVMe is high metadata and provides good random read performance. One of the advantages is the capacity scales with the size of your job. It's also a disadvantage if you're running a smaller job, you have a limited capacity. The biggest disadvantage is these are all independent storage namespaces. And so you have an increase on user burden to essentially manage your data. Typically, this comes in when you have data that's bigger than the available storage on a single node. And so you have to either shard your data or replicate your data across multiple nodes. Many of you have maybe heard about some of the previous efforts we've done in the space. So we have Spectral, we have HVAC, which is AI caching, we have UniFiFS, which is for more like checkpoint restart. But those all give you the illusion of a shared namespace over top of node local NVMe. But it is a burden to users to do this. And so our hypothesis is maybe it's better if we just provide a separate storage system that's tailored for AI or ML workloads, and then kind of isolate that from our traditional parallel file system, which is serving the needs of modeling and simulation. And so we hope that if we did this, we could provide better performance to both workloads. So the shared AI ML storage, has a namespace, single namespace, so that eliminates a lot of the usability and capacity limitations of no local storage, and hopefully still, provides benefit by having the non competing workload of random reads and metadata versus what the large sequential that are typically found in modeling and simulation. And the other thing we've seen is at the current scales, exascale class systems, our MTBFs are relatively low. They're on the order of a few hours. And so we do see an actual increase in defensive checkpointing. And so the idea being, maybe we reserve as much of our parallel file system resources for that workload, make sure it's usable and functional, and then isolate the ML random reads elsewhere. So about a year ago, we started thinking along these lines and decided we were going to get some hardware in-house and start evaluating different systems that might be useful for what we call AI optimized storage, or AOS. And so the goal of this evaluation is simply just play around, get experience with different storage systems on the same hardware when possible, and see how they perform on workloads that look like scientific ML and AI. So what we have is a storage testbed and an associated client HPC cluster. So this all sits on a 400 gig NDR InfiniBand network. Not everything is actually connected at 400 gig. So one of the storage systems we have, which also uses our production file storage for our open development enclave, is a VAST storage system. And this is essentially 8C nodes, and those are connected via 100 gig NICs and 2 DBoxes. DBox is basically NVMe over fabrics, enclosures, and some storage class memory. So the servers that we're using for running DAOS, and we're currently running version 2.6.2, is 8 servers with dual Intels, 512 gigs of RAM, and 2 200 gig ConnectX 7 NICs with 10 NVMe's per server. The configuration is 16 engines, 320 targets, and we're using MD on SSD because we don't have Optames or persistent memory. The client cluster is just 16 Xeon boxes, 24 core, 48 thread per 2 Xeons. And then you see the software. We actually got a recommendation from the VAST folks to look at El Bencho. So El Bencho may not be familiar to some of you. This actually comes from the CTO of VAST. It is a distributed, essentially file benchmarking, but it is not MPI based. And so they use kind of client server TCP to distribute the work, but it does support IO threads. When we took that, and it's very configurable, we took that and made configurations that basically do random reads of entire data sets. So you read an entire data set randomly once every iteration or epoch, then you do that 4 times. And we do it for both small files data sets, which basically large data sets consisting of small files, where a small file is either 32 kilobytes or 1 megabyte, or a large file, so a single shared file, where we're doing the random reads on 64 or 512 meg block aligned reads. And then the other thing we're using in this evaluation so far is DLIO, which you've heard about previously. And so just another thing I'll put in there is, so there's the MLPerf storage benchmark. So DLIO is the thing used underneath MLPerf storage. And specifically, we are looking at the ResNet and CosmoFlow models. And their default, we didn't change the configurations provided by DLIO. And then the biggest thing on the slide to take away is this disclaimer at the bottom. Everything I'm showing you right now is initial performance results and not statistically valid. It's basically the best we've seen for single run experiments. Do not draw conclusions from these results. I will say that they are repeatable, but until we have the time to actually run a series and do some statistical analysis, don't draw conclusions. So first off, I'm showing you results from our El Bencho runs where we're reading lots of small files. So I'll explain what's going on here. So this is data for the first iteration. And the way the test is set up is we have an existing pre-generated data set on some storage system. We use MPI file utils to copy that into the target storage system. And then we immediately start up El Bencho. So this is the first iteration of recently copied data. And so you may not see caching benefits from the first iteration. So to explain the axes here, so the y-axis is thousands of files processed per second. And so in this case, we're using the 32K files. The x-axis is our configurations. So it's combinations of number of nodes, processes per node. We do the math for you and give you the number of processes, and then the number of files in the data set. And we're using three different data set sizes, so 256K, 512K, and a million files per data set. And so the interesting things for the first iteration here is we're using DAOS via DFS in 2 modes. So we're using both interception libraries. So the IO, the original one that came with 2.4, and the PIL for DFS, which came with 2.6.
And sorry, I'm sorry to interrupt you, Mike. This is using El Bencho, or?
This is all El Bencho.
Okay, thank you. Sorry, continue.
No problem. So one interesting note here is both IOIL interception and VAST, which we're comparing against, show kind of a stepwise behavior when we increase the node counts. So if you look at the bottom, you see where it goes from 4 to 8. You can see that the relative performance, jumps up a level. The other thing that's kind of interesting here is, VAST doesn't have any, increased performance from increasing the number of files in the data set, whereas we do see that for both DAOS interception methods. And the other thing we did for you is calculated the bandwidth rate. And so you'll see that, roughly 84,000 files per second equivalent is about 2.6 gigabytes per second. So moving on to the subsequent iterations. So this is of the 4 iterations, iterations 2 through 4, and this is the average performance on each one of those iterations. And so what we see here is VAST shows roughly a 2.2 times bump versus the first iteration. So they are seeing some caching benefits. We still see the roughly step behavior for increasing from 4 to 8 nodes. And the pill for DFS performance is much more consistent across the different data set sizes. And so in kind of the benefits of caching, we get up to roughly 3 gigabytes per second with pill for DFS. So some of you may have noticed the missing plot point in the middle here. That's one of the cases where we hit one of the bugs we're working through. So this is a case where we occasionally run into defuse hanging on our client systems, and we're still working through that. Some of you may have seen that conversation on the Slack. Okay, moving on to the 1 megabyte files. This is the first epoch again, the first iteration. So the performance for VAST again, it was very similar. It doesn't matter. It doesn't seem to do any better for larger files. We do see a little bit increased performance from both IOIL and pill for DFS. And so here we're seeing up to 78 gigabytes per second. So across eight servers, that's decent. So if the servers are going to provide us 200 gig, we should see what is it, divided by 8, so 25 gigabytes per second per server. So we're doing better. And then for the rereads, essentially the later iterations, we increase that a little bit more. You get a little over 10 gigabytes per second per client node or per server, however you want to look at it. So the interesting thing here is, at least in the VAST results, we're seeing some sort of degradation for the data sets that have 1 million files. So my guess, although this needs to be verified, is we're getting past the amount of data that they can cache in either their D boxes or C nodes, and so there's a fall off there. But again, the performance of IOL and pill for DFS is relatively consistent for the small file rereads. Okay, so this is the large file. So essentially doing random IOPS within a single shared file. The first iteration. Here we see the difference is, so the difference between IOIL and pill for DFS is pill for DFS runs much more of the metadata operations through libdfs directly rather than relying on the fuse mount. In the case of a single shared file, it doesn't matter so much because you're not doing very, very many file operations. And so the IOL performance is much closer to what we're seeing with pill for DFS. And the interesting thing here for VAST, we don't have all the data yet, but it seems to decrease with the size of the shared file. So we're going up to 6 terabytes, and then it just keeps going down. And same for reread. We have some noise there in the middle that, again, these are single run results. So it could have been hiccups. We'll see if it's repeatable. But again, IOL and Pilfer DFS is relatively comparable performance per shared files. I will state at this point, since I didn't mention it earlier, these are POSIX containers default settings. We're not using any redundancy because the way we're thinking about this as kind of an AI appliance situation is, it's not long-lived data. So we will probably have to have something where we're copying in data and then running, and then the data leaves. And so data redundancy may not be as important. So right now we're just testing the performance without replication or EC, essentially. We do have plans to test with different redundancy factors. So the last thing I'll show you is the DLIO results. So one thing to note here is these are running against just straight old fuse. We're not using either of the interception libraries, mostly because of time. We just haven't gotten it integrated into our testing harness. I briefly tried to look into the support for TensorFlow and was not able to quickly and easily modify DLIO to utilize the support for TensorFlow. So what you'll see here is ResNet on the left and CosmoFlow on the right chart. You can see the parameters of those data sets. So there's two ways to interpret these results, and you can be either optimistic or pessimistic. So one is, and we saw this with the previous talk as well, is DAOS via just fuse is slow, and you should probably just avoid it. But the other way to look at these results is even the slow option is competitive with fast for, at least on 4 nodes up to, 8 processes per node. So far, so good. So our early results support DAOS as suitable for our scientific ML AI. We do plan to run a bunch more experiments, put this out in a paper, and release our evaluation software. And at this point, I'd just like to thank the team. There's about 10 of us who have been working on this, and a lot of them are on the call. So thanks, everybody. And